Physical engineering systems are rarely static. Whether it's a bridge cable vibrating under load, real-world structures are defined by continuous motion. To mathematically model those dynamic systems, engineers need a specific language. They need equations that can capture rates of change natively, curve changes over time. That new expression is a differential equation. By strict definition, it is any equation that contains a derivative or multiple derivatives of an unknown function. Inside that derivative operator, there are two distinct variables: the dependent variable, which is the unknown function we want to solve for, and the independent variable, which is what we are measuring against. Before an engineer can apply an integration method to solve a differential equation, they have to read its structural parameters. That diagnostic process begins by counting exactly how many independent variables are at play. That initial count forces a primary taxonomic fork for all differential equations. We check the number of independent variables to determine which rules apply. An equation is classified as an ordinary differential equation, or ODE, if all of its derivatives are taken with respect to a single independent variable. This expression shows a standard ordinary differential equation. When we unpack the shorthand y prime notation into dy over dx, we can see the single independent variable is x. The alternative is a partial differential equation, or PDE, containing derivatives against two or more independent variables. By placing a PDE on the right, the structural difference becomes visible. The partial derivative operator evaluates against separate variables, x and y. The analytical tools required to solve PDEs are highly specialized. For our current framework, we are focusing strictly on ordinary differential equations. Confirming that a single independent variable exists is the mandatory first filter. Once an equation passes that test, we can measure its complexity using order and degree. With our equation confirmed as an ODE, we determine how deep the differentiation goes. We call this measurement the order. The order of a differential equation is the highest level of differentiation present anywhere within the expression. We can use this mixed notation equation to see how to scan for the order in practice. We evaluate the level of differentiation for every term. The y prime is a first derivative. Inside the sine function, the y double prime is a second derivative, and the leading term, y triple prime, is a third derivative. The highest value we found during that sweep dictates the classification. We isolate the third derivative, marking this as an order 3 differential equation. The same logic applies when reading Leibniz notation, the dy over dx format. In this notation, the order is built into the superscripts of the operator itself. Take this standard equation. The second derivative of y with respect to x equals 2x. To locate the order, we check the superscripts placed after the d and the x. These indicate that the function has been differentiated twice. Identifying the order establishes the baseline effort required to solve the ODE. It dictates the minimum number of times a function must be integrated to remove all the derivatives. Once we have the order, we check the second metric, degree. While order measures differentiation depth, degree measures algebraic power. The degree of a differential equation is the highest power of the highest order derivative. Finding the true degree is impossible without correctly identifying the highest order first. This dependency creates a common point of failure. It is easy to spot a visually large exponent sitting on a low-order derivative and assume that number represents the overall degree. This equation is designed to trigger that exponent trap. We can isolate these derivative terms side by side to see the conflict. The eye is immediately drawn to the algebraic power of 5. It looks like the dominant factor in the equation. But the term containing that 5 is only a second derivative. Because it is not the highest order in the expression, its power is irrelevant to the equation's degree. We have to focus strictly on the highest order term, the third derivative. The exponent attached to that specific term is a power of 2. Following the rules gives us the correct classification. This is an order 3, degree 2 equation. Decoupling order from degree ensures that we correctly identify the algebraic structure, which determines which analytical tools we should apply to the system. Real-world engineering models often produce dense, overlapping notation. Parsing them accurately requires a systematic visual algorithm. We can apply that algorithm to this multi-term equation. Step 1. Verify the equation type by checking the denominators. The scan shows a single independent variable, x. This confirms we are looking at an ODE. Step 2. Scan for the order. We ignore all algebraic exponents sitting outside the parentheses. We compare the levels of differentiation, a 5, a 7, and a 3. 7 is the highest value, so we lock it in. This is an order 7 equation. Step 3. Scan for the degree. Focus only on the 7th order term. Its outer exponent is a power of 5. We discard the power of 7 elsewhere, as it's attached to a lower order derivative and has no effect on the degree. Our final result is an order 7 degree 5 ODE. By sequencing the scan from variables to order to degree, even the most nested notation becomes readable. These 3 steps, identifying the independent variable, measuring the order, and determining the degree, form the core of ODE classification. This taxonomy is a structural diagnosis determining how an engineer approaches the mathematics of a system. The order identifies which family of integration methods to use. Solving a second-order system requires different techniques than a first-order one. The degree dictates the algebraic complexity, signaling whether the resulting solution will follow linear or nonlinear behavior. This matrix represents a sorted inventory. Each equation is labeled by its order and degree, pointing toward a specific solution path. An engineer solves a differential equation by first reading these parameters to select the correct analytical approach. These classifications allow the math to mirror the physical dynamics of the system, like the predictable stress levels in a vibrating cable. Mastering this taxonomy allows an engineer to select the right calculus tools to build an accurate model of a real-world system.